Okay, so we're looking at this integral, and we notice that we have a rational function. We have one polynomial here, degree 2, divided by a degree 3 polynomial. And so we're not going to be able to do long division. What we do also notice, though, is that we're unable to factor this term, so we have an irreducible quadratic, which is very much what makes this case 3. And so this is going to be a little bit harder than the last one. But we start off in the same way. We want to set up what our partial fraction decomposition is going to look like. So let's actually just take our rational function. And if we look at the denominator, we have the x minus 2. We have that one term there. And then we have x squared plus 4 is our second term. So we're going to end up here with two different fractions in our decomposition. The first one divided by x minus 2, this is no problem. There's just going to be a constant a in the numerator. In the second one, we have that irreducible quadratic. And we know in the numerator we're going to have to put in a linear term. And so that's going to be bx plus c. And so really what we're looking to do now is to find and solve for a, b, and c. So we're going to do that always in the same way. We take this denominator right here, we multiply both sides by that denominator. So we're going to end up with, on the right hand side, we have multiplication by x minus 2 and x squared plus 4. So we're going to simplify this and see what we have left over. So that's gone from the left hand side, and what we end up now on the left hand side with is just going to be this numerator 7x squared minus 5x plus 6. On the right hand side we end up with a, and a is going to be multiplied, the a over x minus 2 is going to be multiplied by all of this. So really we do notice that the x minus 2's are going to cancel each other out, so we'll see what we have left over. We have a multiplied by x squared plus 4. We do the same thing with the bx plus c term. So we have bx plus c, and this time we notice that it's actually just going to be the x squared plus 4 terms that would cancel each other out. So we have bx plus c multiplied by x minus 2. And now we know we have two methods that we can use to solve for a, b, and c. First we check, are there any nice values of x that we can plug in that are going to allow us to solve for one of those variables. And yes, we do have an option, specifically because of this x minus 2 term. We can plug in x equal to 2 to start with. So if x is equal to 2, that means on the left hand side we're going to have 7 multiplied by 4 minus 5 multiplied by 2 plus 6. And on the right hand side we're going to have a multiplied by 2 squared, which is 4 plus 4, which is going to be 8. And then we have the bx plus c term. We know already that this x minus 2 term is going to be 0 if x is 2, so that's going to just disappear. So we have 8a on the right hand side alone. So really what we have on the left, we have 28. Minus 10 plus 6 is really going to be minus 4. And that's going to be equal to 8 multiplied by a. So really we have 24 is equal to 8a, which means that a is equal to 3. So that's perfect. We have that value of x equal to 2 that allows us to solve for a. However, there are not going to be any other nice values of x here. We can't plug them in to eliminate any of these variables. So really, we don't have much of a choice. What we're going to have to do is sort of take this whole right-hand side and we're going to expand. So we expand that, we see what we end up with. So now, on the left-hand side, we have 7x squared minus 5x plus 6. On the right hand side we have ax squared plus 4a plus bx squared minus 2bx plus cx minus 2c. Now we collect like terms on the right hand side. So let's take a look. Let's take all the quadratics, put them together. So we have ax squared, we have bx squared, so we have a plus bx squared. Then we have the linear terms. The linear terms, all that we have there is minus 2b plus c times x, and then that leaves us with the constant terms. We have 4a minus 2c. So now the idea with this second method is that we know the left-hand side is going to be a quadratic. And the right-hand side then, if it's equal to the left for every value of x, must also be a quadratic, and it must be the same quadratic. So really looking at this coefficient a plus b, this coefficient a plus b of x squared must be the same exact coefficient as we have on the left-hand side, so a plus b must be equal to 7. And we're going to do this for all of the coefficients. We get minus 2b plus c will be minus 5, and 4a minus 2c is going to be 6. That's just equating those there. So let's take a look how this works. And what we end up with, as we said, 3 things. 1, a plus b must be 7. 2, minus 2b plus c must be minus 5. And 3, 4a minus 2c must be 6. Now, normally this would be a bit of a problem. We have 3 unknowns and we have 3 equations. However, we do go into this already knowing from before that a is equal to 3. So that's what we're going to start off with. Using even just the first equation, if a is 3, then that means that b is going to be equal to 4. And now we know a and b, we can find c. Let's start here with the second equation. So we get minus 8 plus c is minus 5. And that's going to give us that c is going to be positive 3. And so now we know a, we know b, we know c. We can go and we can actually integrate. Okay, so we know our 3 values. We have a is going to be equal to 3. We have b is equal to 4. And we have c is equal to 3. We also know that going back to our original integral, so this is what we started with. Now that we know a, b, and c, we get therefore that this integral is just going to be equal to a, which was 3, divided by x minus 2. And we have bx plus c in the second integral, so that's going to be 4x plus 3 divided by x squared plus 4. And now the first integral, this one right here, that one's going to be pretty straightforward. We know that's just going to give us a logarithm. So we end up here with 3 multiplied by ln, absolute value x minus 2. And then we go to the second one, and we know from the last couple videos, every time we run into these irreducible quadratics, they're going to have that linear term in the numerator. We can do the same thing. We can split it up into 2 different integrals. So here we'll take 1, and then we'll have our second one. So we have plus the first integral, and we can take out the constant 4. So it's just going to be x divided by x squared plus 4. With the second integral, I can take out the constant 3, and it's just going to be 1 divided by x squared plus 4 dx. And let's sort of clean that up a little bit. So we have our two integrals. And this first one, we can do it easy sub, u equal to x squared plus 4. On the second one, we could do a trig sub, except that technically we've already looked at the rule for how this works out. It's going to be a variation on arctan. And if you have any questions about that, you can go look at my last video, how to integrate 1 over x squared plus a squared. So let's take a look. Let's set up our trig sub, let's set up our regular sub for that first integral. We have u equal to x squared plus 4. We have du is 2x dx, and we can bring that over to the left-hand side. And then let's go inside. That's going to leave us with 3 ln absolute value x minus 2 from the first integral. With the second one, we do our sub. We end up with 4 divided by 2. So we're going to end up with 2 multiplied by the integral 1 over u du. And with the third integral, we remember that it's going to give us 1 over a, and a here is 2, so it's 1/2 multiplied by arctan of x over a, and again a is just going to be 2. So we don't have to put in the plus c yet because of this integral, which we haven't finished with. But as soon as we do that, we will then introduce the plus c. So we go back, we integrate. This is just the antiderivative of 1 over u. It's just going to be ln of u. So we have 2 ln of u, but we know that u is x squared plus 4. And then our last integral is just 3 over 2 arctan x over 2. We put in the plus c, and that is our final antiderivative.